Did our universe itself evolve? Like some kind of cosmic organism? If so, what could it have evolved from? Was there a parent universe before the Big Bang? By the end of this, you might just believe in multiverses, and you might be convinced that this is the most important idea this century. To get there, I want to bring you on the journey that I went on and started with this content that I'm making on the evolution of everything. From the Big Bang through AI, how did everything come to be? And to tell that story, you have to start with the Big Bang, obviously. And how did the Big Bang happen? Well, the simplest explanation of this story is we don't know. But that doesn't really do it justice. For all the other parts of the story, I tell you why it happened. Why did life start? Why did sapiens evolve from monkeys? Why? And we have answers. Well, because. So I wasn't satisfied with, I don't know. So then I explored, and I actually learned that there is a story here. And that story comes in 3 parts. The first part is, why do the laws of physics seem to have constants that make life and the universe possible? Why is it easy to create stars? Why is it easy to create life? And are the constants of physics fine-tuned? But if we have these fine-tuned physical constants, how did they get that way? So the second idea is that black holes birth new universes, even our own, and that at each new birth, there's a selection for physics constants that allow for more reproduction, for more black hole production. And scientists call this cosmological natural selection. And then third, if we're just a universe in this long, proud lineage of universes, how would we even know that? How do you look at the other universes in the multiverse? And so we'll look at this new data from James Webb Space Telescope, JWST, that just might back up this theory, that black hole production in the early universe happened way before we thought it was possible. So we're going to dive into all that today, and let's start with fine-tuning. The history of physics thus far is determining what the laws are. Things like the law of gravity. That things with mass are attracted to each other. And there's a law defining that force of attraction, which is a function of their mass and how far away they are from each other. And so lots of those laws have constants. With gravity, G is the gravitational constant, and it's equal to 6.67 times 10 to the negative 11th. And that small constant explains why I'm not attracted to my computer screen or my microphone, but I am attracted to the Earth underneath me because the Earth is really, really big. So scientists have found all of these laws and all of their constants. Nice work, scientists. Great job. And if we're a bit of a rebellious scientist, you start to then ask, wait a second, why did all the laws and constants get that way? And what you learn is that we have a bunch of these Goldilocks constants, that these numbers are just right. They're not too hot, they're not too cold, they're finely tuned. And the physicist Martin Rees, aka the Baron Rees of Ludlow, that's how you know he's British, he has a book about these finely tuned constants called 6 numbers. And these 6 numbers are epsilon and n and o and lambda and q and d. And d, I think, is really funny because it's like, oh, thank God we live in a 3-dimensional universe. It would suck if you were 2 dimensions. You couldn't have organs. You couldn't have we couldn't have a pipe from our mouth to our butt, So thank God for that last physical constant. So a surprising amount of these physical constants are just right. And then you say, well, if we have all these finely tuned physical constants, how did they get that way? And that brings us to our second idea, which is cosmological natural selection. That's a tongue twister, baby. Cosmological natural selection. How many syllables? 1. Cosmological natural selection. 11. How did we get these constants? There are a few possible answers. One answer, of course, is God. And that's kind of a hilarious answer for 2 reasons. One is, if you're already this far thinking about science in this way, you usually don't invoke God. If you want to choose the other path, that's kind of fine, where you're like, hey, I don't want to go down all these stupid Wikipedia rabbit holes, and I just want to say that the Earth is special and that God made the Earth and humans. That's kind of fine. That's reasonable. I get that. But if you're gonna do all the work of learning about nuclear fusion and the fine structure constant you should probably just keep explaining things with science at that point. But I think the other reason why this answer of God is funny is because it kind of makes sense. I mean, the other answers that we're going to look at today are like chance or multiverses, and neither of those really makes that much sense either. And so honestly, if you want to say God is the answer, I'm fine with that. So that's the first answer, is God. The second answer is chance. Okay, we have something called the Anthropic Principle, which is essentially just luck, but you're a scientist, and so you need to make it sound smart, so you call it the Anthropic Principle. And it's the idea that experimental observations only happen in universes capable of supporting human life. Third answer, the one that we're actually going to talk more about today, is multiverses, aka Cosmological Natural Selection. And this is the idea that if you have lots and lots of universes, you have selection for universes that are fine-tuned for black hole creation, for black holes and stars and life. And I think the instinct for why this makes sense is because we can ask, well, why does complexity arise in general? And in the past, 150 years ago, we thought with, Darwin's finches, we thought, wow, this is a special beak, very special beak. You know who made it? God. God made this beak. Great work, God. And then we're like, actually, these things that have complexity within them, it wasn't God or something else that designed them. It was just millions of years and thousands of generations that selected for fitness. They selected for that really good beak. And so we've kind of distributed the design thinking that exists in all the complexity around us into the many, many, many generations of life before, because we've been on Earth for 4 billion years, and that's a lot of time to arrive at complexity. So that's where evolution came into play initially in biological evolution, but we can invoke evolution again here, which is to say, well, how does the complexity of a physical constant arrive? And you could say something like God, but again, you can say, wait a second, no, maybe that this thing was maybe this constant was selected for, just like a finch, those beaks were selected for over many, many generations. And there's a book by Lee Smolin that outlined this called The Life of the Cosmos, which, by the way, what a weird title. What a classic physics book title. Life of the Cosmos. That doesn't tell me anything. But the book itself is about the idea of an evolved universe. That universes evolve through a reproductive process favoring these traits, and the traits that they have are these physical constants, and those traits evolve over time and are selected to maximize their offspring. And the idea is that, and again, this is just a theory, is that new universes are created in black holes, and so that's where the offspring comes into play. The singularity of the Big Bang is just like the singularity of a black hole. And so for each new black hole, there's a new Big Bang that emerges and a new universe that emerges in the world. And so over time, the universes evolve for more and more reproduction. You're optimizing, the universe is optimizing itself for black hole production over time. You're kind of trying to have lots of little kids. Like a universe that's becoming more and more rabbity over time and less like, the Quakers. And so they call this a fecund universe, which, again, I think fecund, I'm not sure about that word. Fecundity is fine, but fecund, it sounds kind of nasty. So we have this fecund universe, a universe that is designed for black hole creation, and its physical constants are optimized to maximize black hole creation. So if that's the theory, well, then what do we see in practice? Do we see lots of black holes? And the answer, in short, is yes. There are lots of black holes in the universe. And part of this is because the universe is just big, and so there's a lot of everything. But also there are a lot of black holes. So the numbers are roughly this. Every galaxy has a supermassive black hole in the middle. So if there's about 100 billion galaxies, that's 100 billion supermassive black holes, or SMBHs. So that's a lot. But there's even more than that. The main way to create black holes is through dying stars. And so if you're a big enough star, around 20 times the mass of the sun or more, then you'll collapse into a supernova and a black hole. And these are called stellar black holes instead of supermassive black holes. And our galaxy has 100 billion stars, and around 100 million of them, or around 1 in 1,000, will create a black hole, so 0.1%. So that means, if you add them up, for every galaxy, there's a single supermassive black hole and then 100 million stellar black holes. In other words, the universe is pretty frisky. There's a lot of babies happening today in the universe. And so once I sat with this idea, it kind of helped me reframe the universe as a whole. I think previously I thought, mostly about stars and planets. It makes sense where there's the sun, the earth. And so when I looked out into the sky, I would think, well, how many stars are there? How many planets are there? Which ones support life? What about the Fermi paradox? Why haven't we been contacted yet? And in this frame, black holes are kind of like anti-life. They're these weird special parts of the universe that just happen to be there, that mostly break the laws of physics and also don't support life. But actually, from the perspective of cosmological natural selection, these black holes aren't some kind of weird side corner astronomical object. Instead, they are life. It's how the universe reproduces itself. And so from that perspective, stars and planets and life, we're kind of sidelined. We are unimportant byproducts of the normal reproduction process of universes. It's kind of like the book The Selfish Gene by Dawkins, where once you see the world from the perspective of the gene, a lot of things start to make sense. And it's like that, but for selfish universes, where you say, oh, wait a second, the whole universe is actually optimized for black hole production and creation, and we're just along for the ride. Now here's where it gets even cooler. We can view these two kinds of black holes as part of our current universe's evolutionary journey and as part of the evolutionary journey of all the universes that came before us. So let's look at this awesome image from Julian Goff that helps us explain this. And in this image, you can see there's these 3 stages of black hole production: stage 1, stage 2, and stage 3. And the x-axis is time, where we're going from the Big Bang through to now. And you can see that stage 1, it started with these, roughly 1 trillion direct collapse supermassive black holes. So those are those really big ones, the SMBHs. We got about 1 trillion of them or 100 billion of them. And these black holes started near the Big Bang. Right after the start of our universe, boom, we have a bunch of these supermassive black holes. And then in stage 2, Julian writes, there's tens of quintillions of medium-sized stellar collapse black holes. So we start with the supermassive ones, then we get some of these stellar collapse black holes, and then stage 3 is an unknowably large number of extremely small, technologically produced black holes. We'll get to that one later, but let's start with stage 1 and stage 2. Okay, let's talk about those stage 1 black holes. We know they're massive, and they're not just massive, but they're supermassive. Nice work, physicists. Great naming. They're not just 20 solar masses, but they're more like 1 million to 1 billion solar masses. The black hole in our Milky Way is 4.5 million solar masses, Sagittarius A. The famous black hole picture, that's from a galaxy about 55 million light years away called M87, and that one's even bigger. That's like 6.5 billion solar masses, so that's like a really, really big black hole. And these supermassive black holes that exist in the middle of galaxies, they don't form through stars. They form through what's called direct collapse. And the idea behind direct collapse is that, when the early universe was more homogeneous, you can take this sheet of hydrogen and helium and it could go directly from that high density sheet into a black hole. But later on, when the universe was less homogeneous and also includes heavier elements like carbon, etc., then the density kind of nucleates. It nucleates into these stars, kind of like how clouds form raindrops around dust particles. You would get star formation and instead of direct collapse. So direct collapse is a special way to produce a black hole that was only possible at the start of the universe when the universe was more homogeneous. And this idea of a direct collapse black hole is actually very recent. It started just before the year 2000, 1980s, 1990s, and only in the last decade or so is it more mainstream. Now here is the crazy part. Not only did these direct collapse supermassive black holes form at the start of our universe, as you can see on that graph, it's near the start of the Big Bang, but also the hypothesis is that they formed in the early generations of universes themselves. So you can imagine our great-great-great-great-great-grandmother universes, they also had these supermassive black hole creation, the direct collapse black holes. And the idea is that these direct collapse black hole creation is kind of a simple form of reproduction for early universes. And then only later did we get the more complex kind of black hole creation from stellar collapse. So this is kind of like how on the Earth, for the first 3.5 billion years, we just had simple single-celled life reproducing in a simple asexual way. So you can imagine some of these first early universes that had constants that took the simple hydrogen and helium medium and boom, they directly collapsed that into a black hole. And once you have an early universe that starts doing that, you start to get black hole creation, direct collapse black hole creation. Then if you think about the population of all the universes, you start to have lots of universes that are doing that. You start to have lots of universes that are reproducing from direct collapse SMBHs early in their lifetimes. And only then, once you have all these normal universes reproducing through direct collapse black hole formation, kind of the easy way, then some of those universes, there's mutation at each generation, a mutation of physical constants, and eventually one of those physical constants moves us to stage 2, where we have a universe that has the right constants for star formation and then the stellar collapse black holes. So we get what we see today in our universe, which is the creation of all these different stars, and some of those stars end up creating black holes. And because stellar collapse black holes are so much more numerous than supermassive black holes, that starts to dominate the population of universes. So you can imagine, it's 100 million black holes per galaxy versus just one SMBH per galaxy. And so over time, you see what we have in our universe, which is a bit of early SMBH production through direct collapse and a ton of stellar collapse black hole production later in the universe's life. So yeah, that's what we see. And I think the idea is that in our universe, the early collapse SMBH creation, you can kind of imagine it as a vestigial structure of our universe. It's from an earlier generation, kind of like our tailbone or whatever, where we have this older, simpler time with how universes used to reproduce. And that's been kind of frozen out in black hole creation and universe creation. And then we have future complexity like star formation and stellar black holes that is built on top of it. So we have this idea that the universe might be fine-tuned for black hole production. How would we even test that? Can we look at the other multiverses? It's hard, Well, one kind of testable prediction is whether we see black hole production in the early universe. Something like traditional astrophysics, the lambda CDM model, says that black holes form kind of slowly in the early universe and aggregate over time, while something like cosmological natural selection might say that actually the early universe was optimized for black hole production. And the beautiful part about this is that we sent up the James Webb Space Telescope to look at the early universe. What did it find? Well, the James Webb Space Telescope, aka JWST, is such an amazing and beautiful thing. It's about 5 or 10 times bigger than Hubble. Its mirrors are that much bigger. And so it can see longer wavelengths. It can look into the infrared wavelengths. And when things are further away, the light from them has been moving through our expanding space-time for longer, which makes that light more and more red-shifted. And so that kind of allows us to see further back in time. When we have a bigger set of mirrors and a bigger lens on JWST, it can see longer wavelengths and so it can see further back in time. So the question was, will we see these supermassive black holes from the early universe? Was it going to be pretty late in the universe, like a billion years after the Big Bang? Or was it going to be a lot earlier, like 500 million years after the Big Bang? And the answer was, voila, yes, we found a supermassive black hole from only 500 million years after the Big Bang. That's crazy. This thing is called UHZ1, and part of the reason why it's crazy is because it's so early. We know it must have been direct collapse. There wasn't enough time to do this sequential process of aggregating star mass. No, it just, boom, happened super quickly and directly from hydrogen without going through stellar star formation. And the other crazy thing about it is that this black hole, it's 30% of the whole mass of the galaxy it's in. It's 40 million solar masses in a galaxy, a pretty small galaxy, a dwarf galaxy of 140 million solar masses. So it's only like 30% of the whole mass. And usually these SMBHs, these supermassive black holes, they're usually like 0.1% of the whole mass, not 30% of the mass. And so that also tells us that almost all of the gas around there, boom, it directly collapsed into this supermassive black hole. So that's very cool. There was a prediction that said, you know what? I think we're going to find, when we look deeper back in time with the James Webb Space Telescope, I think we're going to find supermassive black holes that were formed through direct collapse, and we're going to find them earlier in the universe than we expect. And one of the possible explanations for all this is because the universe was optimized for black hole creation early. So let's conclude by talking about what this means for astrophysics and also what this means for us here on Earth. Okay, so today we tried to answer whether there was something before the Big Bang. And in the end, we don't know. But I'm pretty tempted by this multiverse theory. That first, the constants of our universe seem fine-tuned for black hole formation. And that those fine-tuned constants may have been evolved through a process of cosmological natural selection that selected for black hole creation. And that we had this simple form of reproduction and black hole creation in the early universe through these direct collapse black holes. And then later we have this much more complex, much more numerous stellar collapse black holes that happen in later universes. And then third, we looked at, when we shot up JWST up there, we actually found these early direct collapse black holes, much earlier in the timeline of our universe than traditional theories would have predicted. So we have these finely tuned constants that were selected for to maximize black hole production, and that was confirmed by the recent JWST data. That's pretty cool. And what's next then? And so what? Well, first, there are a bunch of predictions that might play out. Julian has this great big list of predictions, and one of them is something like, we're going to find earlier SMBHs, not just 500 million years after the Big Bang, but maybe something like 50 or 100 million years after the Big Bang. And we'll see if these things are true. That's the joy of science, is having a theory, and then hopefully that theory is predictive as we get more and more data that aligns or doesn't align with that theory. And if it is true, then maybe 100 years from now, we're going to collectively agree that, we live in this multiverse. We're kind of a middle generation with tons of parent galaxies above us, and then lots of child galaxies beneath us, and all these black holes in our current universe. And that's a pretty big change, It's almost as important as something like the Copernican turn, where we moved from this geocentric model of the universe to our heliocentric model. In the past we thought, okay, the Earth is the center of everything. And like, no, actually the sun is the center of the solar system. And then we said, wait a second, that sun is actually the same thing as the stars at night. And there's not just a few thousand stars, there's actually 100 billion stars in our galaxy. Whoa. And then we learned, oh my God, one of those stars that looked kind of like a spiral-y star, that was actually a different galaxy. That was the Andromeda galaxy. And oh my God, there's not just one other galaxy, but there's actually 100 billion other galaxies. And so we learned that no, Earth is not the center of the universe. In fact, there's 100 billion stars in a single galaxy, and there's actually 100 billion galaxies total. But even then, we always still thought, we still live in one universe. Until now. Maybe there's billions of universes. And maybe the Big Bang wasn't the start of everything. Maybe it wasn't this kind of special Garden of Eden for our universe. Instead, we are part of this evolutionary process just like everything else. And we're part of this bigger and bigger picture that our universe is just one of many universes. And if that doesn't make you feel small, I don't know what will. So that's one big so what, is seeing ourselves in the multiverse. But the other big so what might even be more important. And so I want to go back to Julian's image here. And if you look at stage 3, it says an unknowably large number of extremely small, technologically produced black holes. And the idea behind this is, why are we around? We don't help produce black holes. Why does life exist? Why do humans exist? And maybe we're just lucky. Maybe the world that gave us all these stellar mass black holes, in star production and then star collapse, that thing gave us the whole periodic table, carbon, nitrogen, oxygen, everything. And maybe it was just the case that chemistry on these water planets like Earth just happens to create life and eventually create something like intelligent life, but it doesn't actually create black holes. It's what biologists would call a spandrel. So maybe we're just this cherry on top, that life in humans are an accidental cherry on top of a black hole cake. Or maybe we are part of a line of intelligences that will eventually create even more black holes. And why would you want to actually create black holes? Well, black holes are very efficient at converting mass to energy. They almost do it at 50% efficiency ratio versus something like fusion and fission, which are closer to like 0.5%. So black holes are like 100x more efficient at mass to energy conversion. And so then creatures like us might want to create them. We've already done energy production with fossil fuels and then with nuclear fission, and we're starting to try to do it with fusion. And so maybe these AIs are going to eventually be able to create black holes for energy. And not only will they create a single black hole, but they'll create tons and tons of black holes, and that is the actual goal of the universe. And so that kind of reframes the current AI intelligence explosion. It's not just some future artificial superintelligence pulling itself into existence by bootstrapping this feedback loop of greater and greater intelligence. Oh, I want to be smart. I want to be smart. That is true. And then eventually I'm going to go solve fusion and whatever and build a Dyson sphere around the sun. Yeah, that all might be true. But the actual goal, the kind of teleology of the universe, is for that intelligence to actually maximize energy dissipation through black hole creation. And so if humans do things for this greater purpose, we do things for God, maybe AIs do things for a greater purpose, black hole creation. Maybe. Thank you so much for watching. This is the first video in a new experiment for me. And I've spent so much time kind of understanding how everything has evolved, and I want to share my learnings with you. And so I'm going to start this series from the Big Bang through today on how everything has evolved, from the Earth to how life formed, Homo sapiens, and everything in between. And this is the first video, which is like, well, how did the universe start? With the Big Bang. It's like, well, actually, maybe even started before the Big Bang. So that's today's video. And I think the next video is going to be about everything from the Big Bang through to the start of Earth. So from like 14 billion years ago through 4 billion years ago. And that's a very fascinating time about the creation of stars and galaxies and the elements and planets. And so if you're excited by that, feel free to hit that subscribe button and be notified when I release it. That's the first note. The second note is, I might be wrong or glazing over many things here. I'm more of a science communicator than an astrophysicist, so feel free to correct me or ask questions in the comments. And the third thing I want to say today is that just thank you. Thank you for watching. Also, thank you to my patrons for supporting me on Patreon. Thank you to the donors of Root, this little one-person university that I run to produce this educational content. And also thanks to all the other amazing people who made content about this. Julian, PBS Spacetime, Anton Petrov, all the actual scientists. I'll link all of that in the description below so you can read more about multiverse theory and cosmological natural selection if you're interested. So thank you again, and see you next time when we dive into everything from the Big Bang until the formation of Earth. Bye. It's not that surprising that the only universes where there is life, we find fine-tuning. I don't know. It's kind of a mid response in my opinion.